Um, okay, so anyway, let's do cytology. Okay, the joke will make sense later on with you, so we'll revisit that joke later on. All right, so some basics. We'll get into all the functions of the cell as we go along. This is just an overview of that. It's the basic unit of life. It's going to help protect and support things. It's going to have some sort of movement. Some of them will have movement, like a little flagellum with a sperm, so to say. You're going to have some communication. Cells going to produce and receive electrical or chemical signals from other things. And it's going to tell that cell what to do inside. We're going to have metabolism going on. Energy is going to be produced, ATP. And we're also going to, I know we're not going to get into the inheritance, but we'll do that tomorrow. I know that definitely we're not going to get to that, genetics and stuff like that, okay? So each cell is going to contain DNA. We'll talk about DNA, but actually if you know about Punnett squares, we'll deal with that tomorrow, okay? So this is a run-of-the-mill kind of cell. There's this big thing in here called the nucleus, and it's going to control everything that's inside the cell. These little orange things over here that have like these undulating folds in here, these are mitochondria. This is what's going to actually make ATP, energy. And there's a bunch of other stuff here. And we're going to get into all this. But I don't want you to think that cells only look like this. They can look like this too. See, it's a different shape. Connected to other two cells on either side. There might be certain things, bumps up here, then there's no connection up there. Cells could be very flat, we call them squamous. They could be hexagonal in shape, like a stop sign. They could be square, they could look like a Smarties candies, they could be like balls, they could be long, they could be star-shaped, football shaped, or very, very long. So cells take on a lot of different sizes and shapes. Even these over here are like amoeboid. Even though they're balls, they do change shape on their own, and we'll talk about those later on. So cells can take on a lot of different sizes and shapes. Okay? But before we do that, let's talk about the cell itself. Let's talk about the cell membrane. The cell membrane is what's going to control things to going inside the cell versus outside the cell. And I think of a castle and a village, and then you have that moat that goes around the village. It's going to allow certain things to come in, okay? So you have to, if there's a little village in there, we have to have, let's say, raw materials coming in, like food and men who are knights and stuff. They got to come home from a tough day at work, fighting those dragons, so they have to come in. But it's also going to allow certain things to go out. It's like, the knights have to leave the place. We have to try and sell our products in other cells or other villages. But it's also going to not allow certain things to come in, like thieves and burglars and warriors and stuff that have come from other places. So we're going to try and block them as much as things shouldn't be leaving. We don't want the little babies to leave the village and go and play with the little dinosaurs over there, right? Not dinosaurs, dragons, sorry. But that's what I'm saying. It's going to allow certain things to come in and out. So we call the cell membrane, it's also known as a plasma membrane. Okay? It's going to divide stuff that's inside the cell, intracellular fluid, and things that are outside the cell, extracellular fluid. And it's known as a semi-permeable membrane, meaning it's going to, as I just explained to you, allow certain things to come in and allow certain things to go out and vice versa. So we got to take a closer look at this cell membrane to see why it does that. So before we go into that, there's something called a membrane potential. A membrane potential, we have a charge outside the cell and a charge inside the cell. And they're not equal. If it was -5 outside and +5 inside, you got a net of 0. There's no charge there. 0 is not a charge. So there's going to be something more outside, something less inside, and vice versa. That difference at rest is what we call a membrane potential, because it has the potential of becoming 0, but it's not there yet. Okay? And that's what the key is when we get into a few weeks from now. We're going to talk about an action potential. Okay? It's more positive outside the cell and more negative inside the cell. And that's going to be a driving force to allow the electrical current to come inside or outside. We'll get into that later. every cell membrane looks the same. Okay? On the outside it looks the same. If I told you to come to my house and every house on my street was all green, there was a pine tree in front, and they all had a white picket fence, you won't know what house mine is. So we're going to put little markers on it. We'll put a windmill in front of houses. We'll put a brown picket fence there. We'll put a number on it like 22. That's what these cell membranes have, so we can tell the difference between one cell and another. They have something called glycocalyx, little markers to help certain electrical signals or chemical signals try and find that particular cell. It looks for that. And these glycocalyxes, they actually are made up of either glycoproteins, glyco meaning carbohydrates or sugars, proteins meaning proteins, or they can be made of glycolipids, which is, again, carbohydrates and fats. You'll get to know these when you do the chemistry, okay? But I'm not going to go into heavy about what carbohydrates are and stuff. You'll get that all in the chemistry when you look at that video, okay? Now, this is what a phospholipid looks like. This is a particle of a membrane, and it's called a phospholipid. A phospholipid is one particle that has a head. It looks like a lollipop with two sticks. There's the head over here loves water, and the two tails that come down here hate water. So we say that this is an amphipathic particle because one part likes something, the other part doesn't. Now, let me ask you this. If I take a beaker of water here, and I put water all the way to the top, and then put a lid right on the top, and there is no air in there whatsoever. If I turn it on its side, I turn it upside down, it doesn't matter. This water is touching down here, the water is touching up there. The water is touching on the sides. There is no air in there. And then I put in one particle, one phospholipid in there. What will that phospholipid do when I drop it in the water? There's no air in there. What would you expect it to do? One part of it loves water, one part of it hates water.
The part that likes water would attract to the water.
But there's water all in there.
Water all in it.
What would you expect it to do? Go what? I didn't hear. You might have got it, that's why. Who said go, it goes where? Who said something?
Go crazy.
Yeah, go crazy. It absolutely will. This thing can't find a stable spot and it's going to move all over here. It's going to swarm all over here. It can't find a stable spot. That's what it will do. Now, if I put 10 of those phospholipids in there, what will it do? Connect how?
The hydrophobic ends will connect to each other, and then the hydrophilic ends will go out.
What will happen is this. They'll line up, they'll go like this. The water will be over here, the water will be over here. These tails hate water. They're going to protect themselves away from the water. I mean, in actuality, they'll go all the way around, though. It'll form this. And this is what we call a phospholipid bilayer, meaning there's two layers of phospholipids there. That's a cell membrane. It's a phospholipid bilayer. Go home and tell your parents what you just learned. We learned about phospholipid bilayers. A cell membrane. Oh, okay. All right. You'll impress people, your friends and family. Go ahead. They'll think you're geeks like me. It's okay. All right. A phospholipid bilayer. Okay. If we had air in there, it would go like this. but there's no air in them. There's water on either side. Form this thing. In actuality, when you look at a three-dimensional thing, it's this. And we're going to talk about these proteins in here in a moment. But this is intracellular fluid, this is extracellular fluid, or intracellular fluid and extracellular. It doesn't matter. There's fluid over here and there's fluid over here. Water and water. The water's not in here. This is the basis, the formation, the anatomy of a cell membrane. Okay? It's what's key. Okay? Now, again, the way it's showing here is here's a phospholipid bilayer. I'm sorry, just a phospholipid. Phospholipid bilayer. You can see it at a zoomed out area. It's all this yellow part over here. You got proteins that we'll talk about in here. And it's going around the whole thing, creating a cell. Here's an easier way of seeing it. It creates here phospholipid bilayers. Water inside, water outside. Intracellular fluid, extracellular fluid. There's no water in between there. Okay? You can see it in a three-dimensional thing, kind of like this. Okay? Fluid in here, fluid out here. Don't worry about these. Well, that's what this is here. You'll learn about my cells when you get the digestive system. I don't want to get into that. But liposome or the bilayer sheet that's over there. So you see how it forms. Okay, and that's another close-up of it also. Lollipop with two sticks. Okay? Now, what other components are there in a membrane? Okay. If we just had this structure like this, it's going to be very fragile. It's going to be moving all over. We sometimes refer to that as the fluid mosaic because it's very fragile. It's movable. It's wobbly. It's wiggly. So what we're going to do is that we're going to tuck in areas with some cholesterol. And you'll learn about cholesterol in the chemistry thing. It's about 20, the membrane itself is made up of 20% cholesterol. And that's what's going to give it some rigidity. It's not going to be like this, it's like this. Okay? And that's what the cholesterol does. So yes, cholesterol is good. Alright? Not that it tastes good, but I mean it's good. It's needed for our cell membranes, all our cell membranes. We need them for steroid hormones and other things. You just don't need an obnoxious amount of cholesterol. Your body makes cholesterol and reuses cholesterol. You don't need the extra amount of cholesterol coming into your body from all the foods. Okay? But cholesterol gives a lot of foods taste. So that's why they put cholesterol in a lot of foods. Okay? Otherwise you'll never buy their brands, and big companies don't like that for some reason. Okay? We also have inside the membranes proteins. We have integral proteins. That's proteins that actually will go through the entire length. And we have different reasons why we have these proteins in there. We'll talk about those in a little bit. So they go through the entire length. Okay? Sometimes these proteins have a little channel, a little hole in it. And a little gate. And they allow certain things to go through it. We also have peripheral proteins, and these are proteins that would be found like halfway through here. So I'm going to erase some of this. The peripheral proteins. We could have them up here, we could have them over here. And if you want to make this full, this could be the extracellular fluid, and this is the intracellular fluid. So this is inside the cell, there's outside the cell. And they may attach to other things. Glycocalyx may be attached to these peripheral proteins. Okay? It could be attachment sites for other things too. Hormones can go on there. We could also have receptors on there and so forth. But we'll get into those. So this is just showing you another view of what I just drew for you up here. Peripheral protein over here. You have an integral protein here. Sometimes it's just solid. Sometimes there's like a channel in there. But these are made of proteins. Okay. So the membrane structure. Now we throw in all these things, and that's what it is. Here's the yellow cholesterol that's in there. Integral proteins in there. Peripheral proteins are down here on the side. Glycocalyx is coming off of some of these. Right, so we're building on this thing. So we have 6 functions. Let's talk about these proteins. There's 6 functions, general functions of the proteins that are found in the membranes. Okay? They can act as receptors. There's our lollipops with the 2 sticks, right? You see it now? Here's our protein. This protein might just stay there, and there's going to be like a locking key. Maybe this chemical can only go where this is. That key has to fit like a locking key, and it fits right in here. It's a receptor. Maybe this comes down here, changes its shape a little bit, and it tells inside the cell what to do, because this kind of pushed the button, okay? So some proteins in the membranes could be utilized as receptors for other things. A ligand is any structure that is going to fit inside the keyhole. Okay? So this is the ligand, and a ligand can be made up of a protein, could be a lipid, could be a chemical, could be a lot of different things. But a ligand is the key. The receptor site is the keyhole, and they have to fit like a locking key. Otherwise, that is not going to do anything in there. You take a key to this room. If it's not the right key, you're not going to open up the door. Okay? Again, for receptor sites, they may, let's say this structure here has to fit into this receptor site here. When it does, it might open up the doors, like over here. Just the way a locking or a key would do for this room. You put the key in, it allows you to open up the door. Maybe this one over here is not going to open up a door, but it turns on the light inside. There has to be a connection. There has to be a connection, and it has to be like a locking key. It has to fit. This was a little bit more complicated, but what basically is happening here, this is what we call a G protein. This is the G protein. If this, whatever chemical this is, fits perfectly in here, it's going to kind of, in an essence, in theory, it kind of changes shape. And there's another molecule here, I'm sorry, this is the G protein. This is just a receptor. But the G protein here has maybe 3 or 4 parts to it. When this changes shape because of this one told it to do that, then this one is going to change shape and allow something to do inside. It's like a domino effect. This touches this, this touches this breaks up to this, and it's a cascade of events that occurs. Very complicated. You'll learn more about this in endocrinology because a lot of the hormones will go through this kind of system. All right, we call it a second messenger system. There's the first messenger. The second messenger is after this happens, this is going to tell something inside to do something. Okay? So hormones do it this way. And the reason why I want to mention it now is because 60% of the medications that are out there in the world are all based on this. If we could somehow block this receptor, or if we could stimulate this receptor, or block this over here, or stimulate this over here, it's going to make the cell do something or not do something, which is the basis of pharmacology. Only 50 or 60% of the medications have something to do with the G protein. Okay, another function is this could be used as an enzyme. Now, if you haven't done the chemistry part, an enzyme is just going to, is a chemical that is going to speed up a certain reaction to occur very fast. And in doing so, the enzyme does not get destroyed and can be reused over and over and over. Okay? We want to melt something. You could let it sit there on the counter. It'll melt. but we could speed it up by putting heat on it and put it on the stove. Okay? The stove doesn't get ruined and could be reused, but it happens to make the reaction go much, much faster. This is an enzyme, is a catalyst, just as the stove is, but this is a biological catalyst. A catalyst speeds up reactions. So this protein could take up this chemical here, go over here, and could break that up into two things, and then we could use them into there. This would break up by itself, but it might take a few hours, if not a few days. But if there's in the presence of an enzyme, it will speed up the process astronomically. Some of them will be carrier proteins. Here it looks like a star-like structure, and it won't be able to fit nicely into the channel that it needs to go through. But in this particular channel, it fits like a lock and key inside there. It's specific. So it fits in there like that, and then it pushes it in. So it kind of carries the protein, carries that whatever that is, the chemical inside. It kind of carries it in there, okay? We could have channels, and the channels can be non-gated or ion channels. They're always open, okay? Similar to what this is. You see how there's a gate here? Well, let's say the gate is always open, okay? Now we have a gated channel. So what I showed you before, didn't have a gate. Now there's a gate on this one. And it can be open or closed. In this case, on the board here, it's showing that they're open. There's two types. There's ligand-gated channels. Ligand-gated channels means that something has to be bound here. And maybe when something binds to this channel over here, then the gate is going to open. The door is locked, but you got to put in a key, turn it, and then it opens. That's what this is. Ligand-gated channel. We could also have a voltage-gated channel. When the volt is very high on there, it will open up. You know how sometimes maybe doors, they'll open up when you push in a little keypad, and it makes you don't know what's going on, but inside there it makes the connection, the volt being very high, and that actually opens up the door. So you could have a key, an old-fashioned kind of key, and open it up, so something can bind to it and open it up, or the charge could actually open it up. If it becomes very positive over here or negative over here, that's enough to open up the gate. Some of the proteins over here could be attached to the glycocalyx, markers, okay? These would be only found on the outside of the cell. You wouldn't find glycocalyx and these markers inside the cell. There's no reason for that. You got to go outside the cell so something could recognize that. And this allows for intercellular communication with other cells. We could also use, here's the proteins, they could be attached to other things, maybe inside the cell, to kind of make it sturdy, all right? We have attachment sites, and things could actually bind to it. We put studs in the walls. That allows you to put sheetrock up. You could put them on there. So these are kind of like the studs in the walls, and then we could put things attached to it. Okay? So those are functions as an overview that we're going to talk about with proteins in the cell membranes. Now, let's talk about allowing things to come in and out of that cell. Because it's not allowing everything to come through, it's allowing some things. So why is it allowing some things and not everything? So we're going to talk about what we call cell transport mechanisms. How can you transport things into the cell and out of the cell? Okay? So moving through the plasma membrane, we could break this up into two things. It either is going to need no assistance at all and is able to do that naturally. If the gates are open, they'll just come in. or it's going to need some sort of assistance, some kind of push doing that. So the ones that don't need assistance, something called simple diffusion, osmosis, and filtration. These are naturally occurring kind of things. All right, as much as I take my pen over here, it naturally wants to fall down. Okay, naturally. If I need to put it back up there, I'm going to have to use energy, assistance from energy to move it back up there. Okay? These are the things that need some kind of assistance. Facilitated diffusion, active transport, and secondary active transport. We don't usually call it primary active transport, although we would know what you're talking about. But if we're using secondary, people ask, well, where's primary? And that is the primary. So we'll get into this now. All right, so this is the overview of all the different things that we'll be talking about. So the non-mediated transport mechanism, simple diffusion. Simple diffusion means that we're going to go from a high concentration to a low concentration. I use that example when we had 50 students in the room here and we had 2 students in the hallway there. You've already told me that yesterday. When the doors open, which way do the students want to move out or move into? They want to go from a high concentration, 50 students, to a low concentration until it becomes 25-25. All right? So it becomes equal. Okay? Best way I could explain this too is, let's get a little bit gross. Let's say I flatulate over here. Okay? You're all thinking, like, is he really going to do it? No, I'm not going to do it. Just imagine it. And I don't really mind. It's kind of weird to give you that mental image, but I think this will work out. Okay? Let's say over here, I'm going to flatulate. Okay? When I flatulate, your name's Alyssa. Good answers. You're getting good answers already, right? Alyssa's not going to be too happy. Okay? But all the way over there, what's your name?
Fema.
What is it?
Fema.
Fema. Fema? Obama?
Feva.
Oh, Faba. Faba. Sorry. Okay. So Alyssa, and Faba. Alyssa's not going to be too happy because it's going to be very concentrated over here. Faba is saying, what are you talking about? I'm very comfortable over here. Not for long. Okay? Because over there, it's not concentrated. Just the smell of it is going to be here where it's concentrated, and it's going to find where it's less concentrated. That's diffusion. Going from a high concentration to a low concentration, and then everybody will smell the wonderful aroma throughout the whole room until it's equal. But soon after that, you don't smell it anymore. You just get immune to it. And we'll talk about that when we get in the nervous system. Why, let's say, homeless people, they don't really smell themselves anymore. They get immune to it. But you sure as hell, how could they not smell it? That kind of thing. So we'll get into that when we get into the nervous system. That's another subject. I don't even know why I threw that in there, but that's what's happening. Okay, so it's going to go from a high concentration to a low concentration. And it could be things like ionic charges. If there's, if there's 400 plus charges here and 2 plus charges over there, the positive charge is going to go out there. So it doesn't matter if we're talking about organic substance or ionic charges. As long as the membrane is going to allow that substance to go through. I mean, if there's a brick wall here, Faba will not smell it at all. See what I mean? But if there's a screen, she's going to smell it. Okay? So don't worry. Everyone will get to smell it. All right? Now, one other thing I want to mention. Water-soluble stuff. Keep in mind that these orange things, these lollipops with 2 sticks, likes water on the heads, but hates water in the middle. So what happens here is water-soluble stuff. If this is a water-soluble thing, it won't be able to go through here because in here it hates water. So water-soluble chemicals won't go through there. All right, does that make sense why? Okay? They need to go in, but they have to go through a channel. Okay? Then we have water insoluble things, like lipids, fats. Okay? Inside it doesn't like water. So fatty things, water insoluble things, are able to pass through there, no issue. If it's a water soluble thing and it's rather small, it may still get through. If it's a lipid soluble thing but rather big, it won't go through. So that's why I put water soluble and larger ligands, they can't get through there. Water insoluble and smaller ligands will be able to get through. Think of this as like the Hudson River between New Jersey and New York. All right, certain things can go through that water to the other side. Boats, submarines, right? Those are your fat substances that can do that. But cars, motorcycles, going to have a problem. They have to go through a tunnel. They can get to the other side, but they have to go through a tunnel. Okay? Or a bridge, but we'll use tunnels. Okay? Going from a high concentration to a low, it may pass through here. From a high concentration to a low, it's water soluble, it has to go through a channel. Not bad? You put a pill in water, it's going to be very concentrated, and it will disperse all through here until it becomes equal. From a high concentration to a low concentration. That's how gas exchange works. Okay, this is inside your lung. You breathe in a lot of oxygen, a high concentration of oxygen, in your blood vessels because it just left your cells. There's low concentration there. So it's just simple diffusion. It's going to go from a high concentration to a low concentration. And carbon dioxide is very high in your blood vessels, but very low that you're breathing in. It's going to go from a high concentration to a low concentration, and you blow off the CO2. Okay? Question about diffusion? Okay. Osmosis. Osmosis is diffusion. Don't get confused with it. It's not another thing. It's just going from a high concentration to a low, just the way we saw it. The only thing is, diffusion could be anything. Could be paper balls, could be kitchen sinks, could be people, could be ions, could be anything. Osmosis is specifically water molecules. That's it. And it's going to go from a high concentration of water molecules to a low concentration of water molecules. Okay? Now, there are certain channels that the water molecules have to go through. They're called aquaporins. They're water channels. Whoops, sorry. Okay? And it's going to go from a high concentration to a low. These channels are always open. So osmosis, two ways that it can go. It can go through these aquaporins, which happens much quicker, but the phenomenon is, for some reason, water can also pass through here, not very well, but they can pass through here also. It's a phenomenon that we still don't understand. Okay? But it's not very efficient. That's why we have these aquaporins that happen much quicker. Okay? So, you have these aquaporins, here's your water molecules, most of it's going here, occasionally they'll go through the phospholipid itself. A phenomenon we're not too understanding too much. Okay? Questions about that one? Alright. Now, let's talk about solutions. Here's some definitions. Solute, solvent, and solution. My best example is lemonade. Water is the solvent. The crystals, you're going to make Crystal Light lemonade, right? The crystals are the solutes. When you mix it all together, you got a solution. Okay? Our natural solvent in our body is water. Now, let's talk about hypotonic, hypertonic, and isotonic. Hypotonic is that